Okay, so last time we said that we have theorem, a lemma, which says that every permutation where betas are two cycles, then R is even. Okay, so every permutation is a product of even two cycles. Now it should be always even or always odd. Okay, and now we define the definition of even and odd permutations. Let me use this pen color maybe. So even and odd permutations. Right. Now, a permutation that can be expressed as a product of an even number of two cycles is called an even permutation. Okay. Similarly, a permutation that can be expressed as a product of an odd number of two cycles is called an odd permutation. Right. Now, theorem 5.4 and 5.5 together show that every permutation can be unambiguously classified as either even or odd. The significance of this observation is given in theorem 5.6. So theorem 5.6 says even permutation form a group. Even permutations form a group. Perfect. The statement is the set of even permutations in Sn forms a subgroup of Sn. The proof is exercise, and we will do it in the exercise part. Now, the subgroup of even permutations in Sn arise so often that we give it a special name and notation. So we call it, and we define it in a definition, we call it alternative group. Alternating group of degree n. Definition says the group of even permutations of n symbols is denoted by an and is called the alternating group of degree n. Perfect. Now, the next result shows that exactly half of the elements of Sn, where n is greater than 1, are even permutations. And it is very interesting. So the next result shows, which is theorem 5.7. The statement is for n is greater than 1, an has order n factorial by 2. Now, Sn had the order n factorial, then an has the order n factorial by 2. We can prove this result. The proof says, let's say for each odd permutation alpha, the permutation 1 to alpha is even, and by the cancellation property in groups, we can write that 1 to alpha is not equal to any 1 to beta when alpha is not equal to beta. Thus, there are at least as many even permutations as there are odd ones. Okay. Now, on the other hand, for each even permutation alpha, the permutation 1 to alpha is odd, and 1 to alpha is not equal to 1 to beta when alpha is not equal to beta. Thus, there are at least as many odd permutations is there are even ones, right? It follows that there are equal numbers of even and odd permutations, since order of Sn is n factorial. We have order of an is n factorial by 2. That's it. Okay, that is the proof for this theorem. Okay, perfect. So we have alternative group who has order n factorial by 2. Very nice. Now, from where these names are coming from, like symmetric group and alternative group, how we know that these are the names of these groups? So we analyze something which is very trivial but interesting. So we say that the names for symmetric group and alternative group of degree n come from the study of polynomials over n variables. Assume a symmetric polynomial in n variables. Assume a symmetric polynomial of n variables x1, x2 to xn is the one that is unchanged under any transpositions, is the one that is unchanged under any transpositions. Okay, transpositions of two variables. Transpositions of two variables. And what is the alternative polynomial? An alternative, actually this should be a symmetric polynomial. A an alternative, I think, polynomial is one that changes signs under any transpositions, under any transpositions of two of the variables. For example, okay, for example, the polynomial x1, x2, x3 is symmetric, but the polynomial x1 minus x2, x1 minus x3, x2 minus x3 is alternating. Since every member of the symmetric group is the product of transpositions, so since every member of the symmetric group is the product of transpositions, the symmetric polynomials are those that are unchanged by the members of the symmetric group. The symmetric polynomials are those that are unchanged by members of the symmetric group. Symmetric group, likewise, since any member of the alternate group is the product of even number of transpositions, likewise, any member of the alternating group is the product of even number of transpositions, right? The alternating polynomials are those that are unchanged by members of the alternating group. Perfect. Now, the alternating groups are among the most important examples of groups. The groups A4 and A5 will arise on several occasions in later chapters, and in particular, A5 has the great historical significance. Now, the geometrical interpretation of A4 is given in example 10, which I will present now, and a multiplication table of A4 is also given in table number 5.1, which I will draw and write now. So we have example 10, which is the rotations of a tetrahedron. tetrahedron. Okay, so the 12 rotations of tetrahedron can be conveniently described with the elements of A4. There are 12 rotations of a regular tetrahedron, and can be described as elements of the alternative group on 4 elements. The top row of the figure 5.1, which I am going to show now, now first let me give you the table 5.1. So the table 5.1 is the alternative group of group A4 of even permutations of 1, 2, 3, 4, and we have the notations we are using for this one are, we can mention here that in this table the permutations of A4 are the following, are that alpha 1 is the identity permutation, alpha 2 is the permutation 1, 2, 3, 4, alpha 3 is the permutation which is 1, 3, 2, 4, and alpha 4 is the permutation which is 1, 4, and 2, 3, and then alpha 5 is the permutation which is 1, 2, 3, alpha 6 is the permutation which is 2, 4, 3, alpha 7 is the permutation which is 1, 4, 2, alpha 6, 7, alpha 8 is the permutation which is 1, 3, 4, alpha 9 is the permutation which is 1, 3, 2, and then alpha 10 is the permutation which is 1, 4, 3, and alpha 11 is the permutation which is 1, 2, 3, 4, and finally alpha 12 is the permutation which is 1, 2, 4. Perfect. These are all the elements inside A4, and we note them with these alphas, from 1 to 12, right? And then and an entry k inside the table represented by alpha represents alpha k. Now, an entry k inside the table represents permutation alpha k. Okay, perfect. Now let's give you the table. So we'll write here alpha 1, alpha 2, alpha 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And we have alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, 6, 7, 8, 9, 10, 11, and 12. Perfect. Now I'll fill few of the elements and then I will leave. Draw better lines using this. Perfect. I don't think I have to draw that way, but this is fine. Let's use black. So the first one, alpha 1 compose alpha 1 would be 1. The first row would be same. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Similarly, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. Now, second one, alpha 2 compose alpha 2 is what? Alpha 1. Okay. Similarly, alpha 2 compose alpha 3 is alpha 4. And then 3, and then 6, and then 5, and then 8, and 7, and then 10, and then 9, and then 12, and then 11. Perfect. Similarly, let's go down. Alpha 3 compose alpha 2. Alpha 3 compose alpha 2 is 4, then 3, then 8, then 7, then 6, and 5, and then 11, and then 12, and then 9, and then 10. Similarly, we can fill this out, the whole table. Okay. I can give you alpha 3 compose alpha 3, which is 1. Okay. And then again, I can give you alpha 4 compose alpha 4 is 1. And then 1, and then 1, 1, 1, 1. Okay. That means on the diagonals, we have 1. Not actually. And that's my bad. A very wrong implication. This is true until F4, alpha 4. How can it be? If that is the group, it's not a group even though. So we are true until alpha 4, but then we have something else. So let's fill it out until 4. So we say alpha 3 compose alpha 4 is what? 2, then 7, then 8, then 5, and then 6, 11, 12, 9, 10. And similarly, alpha 4 compose alpha 3 is 2, 2, 1, 8, 7, 6, 5, 12, 11, and 10, 9. And then you can completely fill this table with all of the entries. What do you need is to just compose these permutations, which is already given to you. Okay, that's the homework. Perfect. Now what we want to do? Now I want to talk about their rotations. Okay. Forgive my drawings. Okay, let's draw the numbers first. So we have 1, 2, 3, 4. Okay, and this is A, A, this is B, this is B, and this is C, this is C. Edges, this permutation is the identity permutation. Nothing changes, right? Now we have, then we have 1, 2 here, 3 here, and 4 here. And what you actually did? The permutation over here is 1, 2, 3, 4. That is alpha 2. Okay. And what you actually did is that you have a line from here to here. Should go from here to here. Okay, and it should cut here. Okay, and the movement is like this, right? So you're rotating in this motion. Okay, then we have 1 fixed, 4 is here, 2 is here, 3 is here. Okay, but you are rotating now, but the letters inside this. Now this part is B, this part is also B, this one was C, this one is A, and this one is D and D. Now in this permutation is 1, 3, 2, 4. And when you do that, you move C to this place, you fix B, not fix B, but move it also. Your D becomes here and your A becomes here. And you have line, this kind of symmetry, which does this. Okay. Similarly, when you have the other rotation, which which says 1, 4, 2, 3, these numbers are same, but the parts of the tetrahedron changes. C, A, and this becomes B to B, and this changes what? This changes. Okay, this is this kind of rotation. Perfect. Then we have the permutation, which is the edges are there. Permutation, which we have 1, 2, 3. Okay, and now we move from We move from there to here, and this rotation is like this. Okay, and parts are A, D, B, and B. Right. Then we have 1, 3, 4. Okay, and we move it like this. Okay, and the tetrahedron parts are B here, A, A, and then this is going to be C. And then the permutation we have is 2, 4, 3, 1, 2, 3, 4, and now we move along this line. And we remove this so that I can draw. So the permutation now we have this is 1, and the permutation is 2, 4, 3. We're moving this side to this side, rotating along this axis. So we keep A here, B here, C here, D here, and D here. Perfect. Then we have 1, 3, 4, sorry, this should be 2, 2, 4, and the movement, the permutation, this one is 1, 4, 2, right? And the movement is let me this should go to this line, removing this edge, and here, and the movement is now this way, and the permutation is 1, 4, 2. Perfect. Then last 4 rotations. So 1, 2, 4, 3. The edges in this one are going to be B, B, D, A, C, and C. Now here, we have this, and we move in this way. and this is B, B, A, A, E, C. The permutation is 1, 3, 2. And similarly, we have from here to here, we keep B here, B here, C here, D here, A here, A here, 1, 2, 3, 4, and we move this in the direction that this direction, edge is this one, and 2, 3, 4. Similarly, we have 1, 4, 3, 2, and now we have 3 here, and D, D, A, B, C, and C. The movement comes like this. Okay, and the permutation over here is 1, 2, 4. Last part, this is the area, and this is other one is C, C, B, D, D, A, 1, 4, 2, about that, 3. Permutation is 1, 4, 3, and the movement is like this. These are the rotations of the tetrahedron. You can write, this is figure 5.1, rotations of tetrahedron. Okay, nice. And this is the group which represents these rotations. Perfect. You can explain these rotations in some sense, but you can understand them now. Thank you so much.